we have problem number 1. The equation of tangent to the curve fx is equal to 1 plus e to the power minus 2x, where it cuts the line y is equal to 2 is. So we have a curve fx and we have to find the tangent, equation of tangent at point where the curve cuts the line y is equal to 2. So first we have to solve the equation y is equal to fx, where y is equal to 2 and fx is equal to 1 plus e to the power minus 2x. So we have 2 is equal to 1 plus e to the power minus 2x, or we can write e to the power minus 2x is equal to 2 minus 1, that is 1. So x is equal to 0, right? Now at x is equal to 0, let us find the value of fx, that is y. Y is equal to f0 is equal to 2, right? Because the line is y is equal to 2. So at x is equal to 0, the point of intersection is 0 and 2. This is the point of intersection. Now at this point we have to find the tangent on the curve at curve fx is equal to 1 plus e to the power minus 2x. So first we have to find f dash x, which will give us the slope of that tangent. F dash x is equal to 1. The differentiation of 1 is 0 and the differentiation of e to the power minus 2x is minus 2 e to the power minus 2x. So f dash at x is equal to 0 is minus 2. So we have the equation of tangent as y minus y1, which is f0 is equal to x minus x1 times f dash x, where f dash x is equal to 2 and x minus x0, which is x minus 0, right? So we have y minus 2 is equal to minus 2x, or we can write 2x plus y is equal to 2 as the equation of tangent. So from here we are getting option B as the correct one. Okay. Let us move to another question. If a line ax plus by plus c is normal to the curve xy plus 5 is equal to 0, then okay, we have to find the condition for which the given line x plus by plus c is equal to 0 is normal to the curve. So we have the equation of a curve as xy plus 5 is equal to 0, right? Or we can write it as y is equal to minus 5 upon x. So if we find dy upon dx, we will be getting minus 5 upon x in differentiation of 1 upon x, that is minus 5 times minus 1 upon x square, which is equal to 5 upon x square. So this will give slope of tangent to curve y is equal to minus 5 upon x at any x. Now the slope of normal is minus 1 upon slope of tangent, which is equal to minus upon 1 upon 5 upon x square, which is equal to minus x square upon 5. So the slope is always negative. Slope of normal is always negative, right? So we have the equation of line as ax plus by plus c is equal to 0. So if we find the slope of this line, then by is equal to minus ax plus c. This is minus c, right? Or y is equal to minus a upon b x plus minus c upon b. So here, from here we can see that slope is minus a upon b, okay, which is always less than 0, right? That means a upon b should be greater than 0, which means a is greater than 0, b is greater than 0, both, or a is less than 0, b is less than 0. So either this or this must satisfy the slope of normal as negative. So we have the option as a greater than 0, b less than 0, which is incorrect. B greater than 0, a less than 0, which is also incorrect. A less than 0, b less than 0. This is correct. So we have C as a correct option. Okay. Now moving to the problem 3. If S is the interval such that fx is equal to 8x square minus ln mod x increases in s, then s contains. So we have function fx which is equal to 8x square minus ln mod x. So if we evaluate, clearly here the domain is x greater than 0. So f dash x, if we calculate, then we will be seeing the value is 8 times 2, which is 16x, right, minus 1 upon x. Okay, so for this to be increasing, f x to be increasing, f dash x must be greater than 0, right? That means 16x square minus 1 upon x must be greater than 0. So we have, from here we have, we take common 16, we have x square minus 1 by 16 upon x must be greater than 0, or we can write it as x plus 1 by 4 into x minus 1 by 4 upon x 1 by 16 is greater than 0. So 0, 1 by 4 and here minus 1 by 4. This side is positive, this side between 0 to 1 by 4 is negative, again minus 1 by 4 to 0 is positive, but the domain is x greater than 0. So we are not going to consider less than 0. So this is greater than 0, the quantity is greater than 0 when x is greater than 1 by 4. That is, it lies between 1 by 4 to infinity. So we have none of the options which are getting satisfied. Okay, since there is mod x, we can afford this x to be less than 0. For the function ln x, x should be greater than 0, but since this is mod x, so this is always positive, so we can afford x to be less than 0. That means we can consider the negative part, right? So if we consider the negative part, 0, 1 by 4, minus 1 by 4, so this is plus, this is minus, this is plus, this is minus. So from minus 1 by 4 to 0, this interval, we have the function fx to be increasing. So option A is correct, right? Now moving to the next question, we have y is equal to a log mod x plus bx square plus x has its extreme value at x is equal to minus 1 and x is equal to 2. Then the point a, b is, so we have function fx is equal to a log of mod x plus bx square plus x, right? Suppose x is greater than 0. Let us assume x is greater than 0. Then f dash x must be a upon x plus 2b, right? So for finding extremum values, we have f dash x is equal to 0, because extreme values are those points where maximum or minimum occurs. So we have x plus 2b is equal to, so derivative of fx at x is equal to minus 1 as well as at x is equal to 2 is 0. So we have f dash x as a upon x plus 2bx plus derivative of x is 1 plus 1 is equal to 0. So f dash minus 1 is minus a minus 2b plus 1 which is equal to 0, or we have a plus 2b minus 1 is equal to 0. So let us name this equation as equation 1. And also we have f dash 2 is equal to a upon 2 plus 2 times 2 which is 4b plus 1 is equal to 0, or we can write it as a plus 8b plus 2 is equal to 0. So let us name this equation as equation 2. So now we have equation 1 and equation 2. Solving these two equations, we are going to subtract equation 1 from equation 2 to eliminate a. Equation 2 minus equation 1, 8b minus 2b is 6b, and 2 plus 1, which is actually 2 minus of minus 1, 2 plus 1, 3 is equal to 0. So b we are getting minus half, and if we substitute b in any of these two equations, we will be getting a So I am substituting this in equation 1. So A is equal to 1 minus 2B, which is equal to 1 plus 1 is equal to 2. So we have point AB as 2 minus half. So option B is correct. Now moving to the next question. The number of critical points of fx is equal to maximum of sin x and cos x for x 0 to 2 pi. So let us draw the curve of sin x and cos x between the interval 0 to 2 pi. So this is the curve of sin x. This is 2 pi. This is pi. This is 2 pi. This is pi by 2. This is 3 pi by 2. Now if I draw the curve of cos x, then it is something like this between the interval 0 to 2 pi. So the function is maximum of sin x and cos x. So the function is this, which is maximum, right? So we have fx as this red curve. This is fx. So number of critical points. Critical points is the candidate of maxima and minima. That is a point where maximum or minimum occurs. So this is the point, one point, and this is another point, which is critical in the interval 0 to 2 pi. So we have two critical points, right, for this curve. Now moving to the next question. If fx is equal to mod of 4x minus x square minus 3 when x is belongs to 0 to 4, then x is equal to 1 is a global maximum, x is equal to 3 is a global maximum, x is equal to 2 is a local maximum, or none of this. So we have to check the maximum or minimum for this curve fx is equal to 4x minus x square minus 3. Again let us say fx is equal to, we have 4x minus x square minus 3, or we can write it as minus of x square minus 4x plus 3, or we can have x minus 1 x minus 3, right? So if we draw this curve at 1 and 3, then we will be getting something like this. Okay, so at x is equal to 2, we are getting the maximum value for this curve, right? But this fx is not this curve. Fx is actually the mod of this curve. So we have the curve as something like this, right? So x is equal to 1 is a global maximum. No, this is not a maximum. X is equal to 3 is a global maximum. Again, this is not a maximum. X is equal to 2 is a local maximum. Yes, at point 2 we have a local maximum, and this is not a global maximum because global maximum is greater than this value, right? So we have x is equal to 2 as a local maximum. Okay, using graphically we can solve this problem very quickly, right? Now moving towards the next question. We have the curve fx, which is defined as 3 minus x in the interval 0 to 1 and x square plus ln b in the interval 1 to infinity. So then the set of all values of b for which fx has least value at x is equal to 1 is given by. So say let us find the value of fx at point x is equal to 1. If 1 is ln b, right? Because at x is equal to 1, the curve fx is x square plus ln b. Okay. Now f1 minus is equal to, when x tends to 1 from left hand side, that is limit x tends to 1 minus fx. Then just before 1, the curve fx is 3 minus x. So we have 3 minus 1, which is equal to 2. Okay. First of all, the curve to be continuous, right? We have the condition fx at point x is equal to 1 should be equal to fx at point just less than 1, which is f1 minus, right? But here we have to check for least value occurrence at x is equal to 1. So let us again have a graphical approach. We have a curve y is equal to 3 minus x. So y is equal to 3 minus x up to x is equal to 1. So at x is equal to 1, its value is 2, and x is equal to 0, its value is 3. So up to x is equal to 1, we have this curve, right? And we have another curve, that is x square plus ln b. So we have a curve x square as something like this. Okay, this is x square. This is a curve. This curve is y is equal to 3 minus x, and this curve is y is equal to x square. Okay. So at x is equal to 1, we have to find the set of values of v for which fx has least value at x is equal to 1. Okay. So if we have, say, if we have this value at point x is equal to 1, at this point, if we have the curve which is something like this, say this curve, this curve, this curve. Okay, so let us draw in more explanatory way. So we have a curve. Before 1, we have this curve, that is y is equal to 3 minus x, and just after 1, we have the curve y is equal to x square plus something. So its nature is something like this. Here ln b is negative, right? But we see that we have seen that ln b is only negative for b less than 1, right? Okay. Then this value ln b at x is equal to 1, x square, for a function fx is equal to x square plus ln b. At f x is equal to 1, we have its value ln b. So this ln b must be less than 2, right? Because let us read the question. Then the set of all values of b for which fx has least value at x is equal to 1 is given by. So at x is equal to 1, the function fx is attaining its minimum value. So fx at 1 is equal to 1 plus ln b, right? So we have fx at x is equal to 1, f1 is equal to 1 plus ln b. So this must be minimum, right? So for this to be minimum, we have 1 plus ln b should be less than equal to 2, right? Because this value is 2. So this value should be less than equal to 2. This should not go beyond this value, beyond this, that is 2. So we have 1 plus ln b less than equal to 2, or we can write ln b is less than equal to 1. So from this we have b belongs to 0 to e, right, where e is closed. ln b is equal to 1 at b is equal to e. So from here we have option C as the correct one. Now moving to the next question. Problem number 8. We have if double dash x is greater than 0 for all x belongs to real. F dash 3 is equal to 0 and gx is given by f of tan square x minus 2 tan x plus 4 in the interval 0 to pi 2. Then gx is increasing in. Okay. So we have gx as f of, we can write gx as f of tan square x minus 2 tan x plus 1 can be written as tan x minus 1 square plus 3, right? So if we check for g dash x, we will be getting f dash of tan x minus 1 square plus 3 into differentiation of inside quantity, which is 2 times tan x minus 1 into sec square x. So if gx is increasing, then g dash x must have to be greater than 0. So for g dash x to be greater than 0, we have 3 terms here. One term is f dash of tan x minus 1 square plus 3. Another term is tan x minus 1 and another term is sec square x. So clearly this term is greater than 0. So we have to check for this term and this term. So checking for f dash of tan x minus 1 square plus 3. Okay. So it is given that f double dash x is greater than 0, right? See, it is given in the question f double dash x is greater than 0. So we have f dash x as increasing function, which means that f dash x for x greater than 3 must be greater than f dash 3, which is equal to 0, right? So clearly this value is greater than 3, right? Tan x minus 1 square is positive plus 3. So 3 plus something is always greater than 3. So we have the value f dash of tan x minus 1 square plus 3 is greater than 0, right? Because this is an increasing function. So this must be greater than f dash 3, which is equal to 0. So this must be greater than 0, right? So now we have to check for tan x minus 1. Now for tan x minus 1 greater than 0, we have x to be from pi by 4 to pi by 2, right? So for the interval pi by 4 to pi by 2, the function gx is increasing. So from here, option D seems to be correct, right? Okay. Moving to the next question, we have problem number 9. The function y is equal to fx is represented parametrically by x is equal to t to the power 5 minus 5t cube minus 20t plus 7 and y is equal to 2t cube minus 3t square minus 18t plus 3 in the interval minus 2 to 2 plus 2. The minimum of y is equal to fx. So we have to find the minimum, where the minimum of y is equal to fx occurs, at which parametrical value, that is at which t, the minimum y is equal to fx occurs. So let us find dx upon dt. Dx upon dt, we will be writing 5t to the power 4 minus 5 3 is 15t square minus 20, right? So if you take common 5, you will be getting t to the power 4 minus 3t square minus 4, right? Which can be written as 5t square plus 1 into t square minus 4, which can be written as t square plus 1 into t plus 2 times t minus 2. So dx upon dt is, in terms of parameter t, can be written as 5 times t square plus 1 into t plus 2 into t minus 2. So at t is equal to plus 2 and minus 2, we are getting dx by dt is equal to 0. So, but we are not considering the parametrically value 2 and minus 2, because here it is limited within minus 2 to 2. So this is not equal to 0 for the value of t given, right? Now we are going to find dy by dt. dy by dt is, here y is 4t cube, so dy by dt is 4 3 is 12 t square minus 3 2 is 6t minus 18, which can be written as 6 2t square minus t minus t, right? So for minimum or maximum, whatever to occur, dy by dx must be equal to 0, right? So dy by dx can be written as dy by dt upon dx by dt is equal to 0. So basically we have dy by dt is equal to 0, or we can say that 2t square minus t is equal to 0, right? If we factorize this polynomial, we will be getting 2t square minus 5t, 2t square minus 3t plus 2t minus 3 is equal to 0, or we have, taking t as a common, 2t minus 3 plus taking 2 as a plus taking 1 as a common, we have 2t minus 3 is equal to 0, or we have t plus 1 times 2t minus 3 is equal to 0. So we have t is equal to minus 1 and 3 by 2 as a candidate for maximum or minimum. So we have to check at which point of t, that is at which value of t minimum is occurring, because question in our problem, it is asking that minimum value of y is equal to x occur at. So we have to check at which point, that is is it occurring at t is equal to 1 or is it occurring at t is equal to 3 by 2. For this we have to check for double derivative test, right? So we have d2y upon dt square as, see, dy by dt is the value 6 times 2t square minus t minus 3, okay? So we have dy by d2y by dt square as 6 times 2t square, differentiation of 2t square is 4t minus 1, right? So at t is equal to minus 1, d2y by dt square is coming as 6 times minus 4 minus 1, which is obviously less than 0. So at this point, less than 0 means the curve is concave downward, that is, less than 0 means concave downward is like this, so maximum occurs, okay? And for value t is equal to 3 by 2, we have, for value t is equal to 3 by 2, we have d2y upon dt square as 6 times 4 into 3 by 2 minus 1, which is 6 minus 5, which is equal to 30, that is greater than 0. So we have minimum at this point. So from this double derivative test, we have checked that as t is equal to 3 by 2, we are getting minimum. So from here option B is correct, okay? Now moving to the next question, we have if a function fx is equal to cos of mod x minus 2ax plus b increases for all x, then Okay. See, the function cos of mod x is equal to cos x, right? Because whatever you place inside this, you will be getting same as cos x, as cos x is itself an even function, right? So cos of mod x is equal to cos x. So we can write fx is equal to cos x minus 2ax plus b. So if a function fx increases for all x, that means f dash x is greater than 0 for all x, right? Which belongs to real. So we have f dash x as, in differentiation of cos x is minus of sin x minus 2a, right? This should be greater than 0. Or we have 2a is less than minus of sin x. That is, a is less than minus of sin x upon 2 for all x. So the minimum value of sin x, the maximum value of sin x is 1, right? And minimum value is minus 1. So a should be less than, if we put the minimum value, then a should be less than half. If we put the maximum value, a should be less than minus half. So for all x, if dash x is greater than 0, then a should be less than minus half, right? So here a must be less than minus half. So from here option C is correct, right? We can put the sign of equality because it is not writing strictly increasing, it's just like increasing. So we can have fx is greater than equal to 0 also. So this can be equal to 0 also. Hence we have a is less than equal to 2. Okay, so option C is correct, right?